Hello, everyone. So at the request of several students in this course, I've decided to make a video recording of the lecture. That way you could have both the text and also a verbal explanation of all the concepts that we covered this week. And before we start doing that, I want to take a step back and talk about the study of physics itself. And really the first question you would start at is, what is physics, right? And I came across this quote by a man named Jules Henry Poincare, who says that science is built up with facts, just like a house is built with stones. But a collection of facts is no more a science than a heap of stones is a house. So what he's trying to say is that just random facts, right? Random knowledge, it's no more a science than just a pile of bricks, would be called a house, right? You need structure. You need order. And that's kind of what physics brings to the table, right? It's like the mortar. It's what glues all the sciences together. On a more, intellectual level, physics is really the scientific study of matter, motion, and energy. And what it does is explains the interaction between matter and energy, right? And how that pertains to motion. So it explains really everything. Its goal is to understand how everything in the universe behaves. And so physics can deal with particles and quantum physics to astrophysics, right? The study of galaxies and the universe as a whole. So from the very, very small to the very, very large. And again, our goal is to explain how things work. Now, physics uses the scientific method, which hopefully you remember from probably middle school science, and it uses this method to explain phenomena, or attempts to do so. So you start off with a theory, right, which are formed based on observations, right? These are intelligent guesses, sometimes based on intuition, right? You figure that's how things work. Now after that, you perform physical experiments, which then yield measurements, right? Data that we can measure. Which then will be compared with the outcome that would have been predicted by the theory, right? So we test that experiment back to the theory. And now when a theory reliably predicts the results of experiments, it is said to embody a law of physics. And this, guys, is really the outcome of these experiments, is to obtain scientific laws. Now these are expressed in the language of math. And then these can then be used to predict other phenomena, right? So we built up on these laws. We start small with things that could be easily observed and measured, and then we can continue building up until we can hopefully predict things, again, in outer space, for example. Now, why is physics important? That's sort of the next question, right? So studying the way things move and interact in the world is fundamentally useful. In fact, you use it every day. Our brains have needed to develop an automatic understanding of physics, right? From learning to, how to balance and walking, to being able to cross the street by yourself, right? So let's say you're in the middle of a street, you look one way and there's a car that's 3 blocks away and driving slowly, and you say, oh, I have enough time to cross the street. And then you look to the other side and you see a car that's only half a block away and driving 30 miles an hour, right? And your brain makes calculations about speed and velocity and motion that will, hopefully safely help you cross the street, right? By understanding these concepts. The same as when you're throwing a ball, right? So if you're playing catch with someone, you have a small ball that doesn't weigh much. You don't chuck it as far as you can or as hard as you can if they're nearby, right? You make calculations about the amount of force required and how much speed you want it to catch and all that. So that requires, again, these automatic calculations that they just seem like second nature to us. But again, they're calculations of friction, forces, strength, and speed. Now, furthermore, physics is the most fundamental of sciences, right? From physics, all other branches of sciences have been built upon. Chemistry, which is the study of the interactions of cells, or different different matter, is applied physics, right? And then biology is sort of looking at all these interactions within your body. That's applied chemistry. So on and so forth. So again, physics is sort of at the root base of this. From physics, every other branch that applies to us is built upon. And I think last but definitely not least, for me personally, and for you guys in the future, hopefully, you should know that imaging modalities are governed by physical principles, which must be understood in order to increase their diagnostic value. So what I mean by this is that understanding the laws of physics built in these machines, like in an ultrasound machine, it's important to perform the very best study we can, to take the very best image that we can so that the patient can be diagnosed correctly. So for example, I have patients that are, maybe small children, and I can have a patient that's just a very morbidly obese patient, right? And so these are two very different body types. And the ultrasound machine allows me to change the frequency of the sound signal going into this body to tailor it to the size of the patient, right? So I can change the frequency in order to be able to image each individual patient to the best of our ability. And again, if I didn't know about frequency, if I didn't know about speed of sound, it wouldn't allow me to tailor this parameter to the test. And then I may not be able to get good images on children, or I may not get good images on very large patients, right? So this is going to help me sort of on a daily basis, right? And I use it every day. It's so important, in fact, that, if you're in the ultrasound program, you're going to study for 2 years, right? There's a lot of physics that, needs to be learned, and then there's boards that you'll take eventually once you graduate. And again, they require knowledge of physics for our field. So physics is broken down because it's just such a broad topic. So it's been classified into traditional areas of study. And again, some of these we're not going to cover, like atomic or nuclear physics or quantum physics, right? That's not the scope of this study. But some of the other more classical areas we do, like mechanics, right, which is the study of how things move, or electromagnetics, which is the study of light and radio waves, thermodynamics, light, or acoustics. Again, you don't have to memorize the categories, but just know that often these areas overlap with each other. So there's specific theories that apply to more than one, or concepts that have formulas that are very similar, right? And perhaps the variables change, but the formula is the same. And again, they apply to more than one. All right. So again, prior to this slide, everything I just talked about is just sort of an FYI, little extra information on the side. From here on out, this is kind of the stuff I do expect you to memorize. So we'll start with the fact that, we'll need to make physical measurements, right, of quantities in order to make calculations in physics. And so the first thing we will learn is that physical quantities fall under two categories. So we've divided them into two kinds. The first are what we call scalars, all right? And scalars are parameters, right? Things that have a numerical value, right? Have a measurement, but there's no direction needed. So there's only one way to measure them. Whereas vectors are other physical parameters that have a numerical value, but they also have a specific direction. So I'll explain further, okay? Another way to think of scalars is that they're parameters that have only a magnitude, right? And that's kind of the key word. The word magnitude, you can think of it as size. So an example of a scalar could be speed, distance, temperature, right? These are things that we measure one way and one way only, right? Vectors, on the other hand, are sort of the opposite. These are physical quantities that have a magnitude, right? They have the size, but they also have an orientation, right? Which another way of thinking of orientation is direction. Velocity is a vector because it can tell speed and direction. The word displacement is similar to distance, but it also speaks of a direction from one place to another. Again, we'll explain each one of those individually, but I just want to make that difference. So The first concept, or the concept we're talking about today, is motion. And motion in general is just the change of position of an object with respect to time. So again, there's a change in a place, and it takes time, right? So this is really one of the first phenomena to be studied carefully by civilization. The Greeks called it kinematics, right, which is like the study of movement. And in order to describe motion, it's important to specify the parameters that are needed, right? So motion requires a movement or a displacement, meaning there's a distance from a reference point, right? So if you are moving, you're no longer in the same space, right? You went from point A to point B, and those are two different points, okay? And the other thing that it needs, right, in order for motion to occur, is that you need time. So motion takes place over a period of time. So you cannot get from point A to point B in 0 time. Now you can get from point A to point B in a fraction of a second, right? A millisecond even, but it still takes time. You can't be in point A and point B at the same time. So it requires time. So then motion can be sort of split up into what we call speed and velocity. So let's start with speed. So speed is defined as a scalar quantity that measures the distance traveled, right? We're going to call that d, over the change in time. Okay, and when you see a rectangle, that just means change. It's called delta, so change in time. It's also called the rate of motion. So often some books explain speed or talk about speed and use the word rate, and then we'll use the letter r for its variable. But basically it just says how fast something is moving, right? Everybody knows that concept. Now mathematically, the symbol, again, we're going to use is v, and that's because the equation is same as velocity, okay? But again, you will come across sources that use the word rate and therefore use the variable r, okay? But again, for this class, we'll use v. And the equation is simple. Speed, v, equals distance divided by time. And so because we are measuring distance and dividing it by time, our unit of measurements are going to be any unit of distance over time. So I'll give you an example: miles per hour, right? Kilometers per hour. Now in science, the standard unit of measurement for speed is meters per second. So most people measure speed meters per second. Unless it's something really, really fast, you could say, I don't know, millimeters per microseconds, right? But regardless, the standard unit is meters per second. So I'll give you an example of a question you may come across in a quiz. Okay, hint, hint. If you traveled 12 miles in 3 hours, what speed did you travel at? And so the first thing we look at is, what am I being asked? And usually it comes at the form of a question, right? It's usually at the end of the sentence. Well, it could be in the beginning, right? But it says, what speed did you travel at? So I'm wondering speed. I only know one equation, and again, it's your job to memorize these. It's your job to memorize that speed is v equals d over t. And once you do, you plug in the info you are given. So we're giving something that says 12 miles, and so you should think in your head, okay, miles, that's a unit of distance, right? It's not a unit of time. So 12 goes above, 12 miles. And then I'm also giving 3 hours, which again is a unit of time, and it could be only a unit of time. So we put that at the bottom, 3 hours. So then again, I have this equation, v equals 12 miles divided by 3 hours. Now again, it's important not to get rid of the units because your answer should be in the correct units. It cannot just be a number without units. That's not correct, right? So we know 12 divided by 3 is 4, but you cannot tell me the answer is 4. The answer is 4 miles per hour, or 4 miles divided by 1 hour. Okay, because these two numbers divide into each other, 12 and 3. Oops. 12 and 3 divide into each other, but miles and hours do not divide into each other. So our answer is going to be 4 miles per hour. Alternatively, you may be given some algebraic equations, right? Some digging up to do. So what if I ask you that? What if I tell you an elephant runs for a half an hour at a speed of 6 miles per hour? How much distance does he cover? So again, the question now is distance, okay? And I'm giving time, and 6 miles per hour we know is a unit of speed, right? So I'm given v and I'm given t, but I need d, right? The distance. So that means we're going to use algebra to turn this equation, v equals d over t, to d equals v times t. And again, this is the reason why we went through a little algebra introduction, right? So you could do this. All right, we're isolating d by multiplying by the reciprocal of t, correct? And that's how I got to this. So again, if you have a hard time doing this, then email me, or again, you're gonna have to memorize. You're gonna have to memorize 3 equations rather than just memorize 1. But again, this is something that you should be able to do. After that is just plugging in the the variables. So v is 6 miles divided by an hour, right? We're not going to get rid of that. And then we're going to multiply by half an hour, or 0.5 hours. Now what happens to the hours here and the hours here? They cross each other out, right? Because one's in the numerator and this is in the denominator. So I know my answer is going to be in miles only, which is good because miles is a unit of distance. So again, 6 times 0.5, we know is 3 miles. And I know that because, again, I didn't just ignore my units. I left them there in my mathematical equation. Okay, next we'll talk about velocity. And velocity is very similar. The definition is just that it's a vector quantity, right? We know it's not scalar. It's a vector quantity that measures displacement over the change of time. So basically, it's the rate of change in the position of an object with time. And the difference here is that it tells the speed and the direction. Very important. It tells the speed and the direction. Now, luckily for us, mathematically, it's the same. Symbol is v. The equation is the same. Now, again, sometimes you'll see this where they'll say v equals the change in position or change in displacement divided by the change in time. But again, for our purposes, we'll keep it simple and we'll just talk about the same equation. All right, so again, the question is, how are speed and velocity different? All right, we know that speed, it tells only magnitude, and velocity gives the magnitude and the direction. So here's the difference between a speed equation or a speed question and a velocity question, right? So here's a typical velocity equation. What is the velocity of blood in a vessel that travels 6 centimeters in 4 seconds towards the brain, which in science or in medicine we call the cephalad, right? Now the math is the same. V equals d over t. 6 centimeters divided by 4 seconds is 1.5 centimeters per second. But the difference is that I had to plug in the direction here. 1.5 centimeters per second cephalad, right? Luckily, again, I'm given that. So it's not like you had to figure that out. Again, the important thing is for you to know that if I ask you for a velocity, you should be giving me a direction. Otherwise, 1.5 centimeters per second is only a speed answer. And so it's not correct if I'm asking for velocity. Okay? Again, if a swimmer can swim backwards at a rate of 2 meters per second, how long will it take him to swim 50 meters? How long will it take him? Right? That means I need time. So again, I isolate t and multiply by reciprocals. I get t equals distance divided by velocity. In this case, again, plug in 50 meters. Divide by 2 meters per second, which again, I'm given all these numbers. And then again, cross the meters, my answer is in seconds. Guess what? Time is measured in seconds, so that's good, right? So 50 divided by 2 is 25 seconds. And again, 25 seconds, what? Backwards, right? I just wrote I put in an arrow there, but it just means backwards, right? This swimmer is moving in a certain direction. All right, so in summary, again, I think it's pretty easy. We've learned about speed, right? Speed equals distance over time. We've learned about velocity, which is also v equals d over t. However, velocity is going to also tell me a direction, right? And we're able to solve for distance or for time using these equations, right? So we're using algebra to solve for any of the 3 variables in these equations. And lastly, make sure you understand the difference between a scalar and a vector and be able to give examples. You know, say for example, distance versus displacement, right? Or speed versus velocity. I think an easy way to remember this is that speed and scalar both start with an S, and velocity and vector both start with a V, right? So that's a good hint. All right, guys. Well, hopefully this helped. This is just a silly joke. See you guys next week.